So the generalized Hough transform or general Hough transform algorithm is very easy. If the orientation is known, you know the orientation of the object, you do exactly what I showed you. For each edge point, you compute the gradient direction, you retrieve the displacement vectors r for that direction to vote for the reference point, and the peak in this space, in this case we're only voting in x, y, that's the reference point, that's where your object is. It's the one with the most sort of supporting edges. Now, it's sort of unreasonable that you might know the orientation and the scale. So let's talk about orientation. Okay, suppose the orientation is not known. Well, all we have to do is try the different possible orientations, and that's written here. Again, for each edge point, but now we have what we'll call a master orientation. This is the actual orientation of the object. For each orientation, possible master orientation, we compute the gradient direction, but we subtract off the master. So the master here is this theta star, the actual gradient is theta, but the gradient we're going to use is this theta prime, which is just the gradient with the overall orientation subtracted off of it. And so now we retrieve the displacement vectors for theta prime. So we're still voting, and peaks in this Hough space are the reference point, but notice now that we're voting in x and y and also theta star. So you remember that space complexity, which was k to the n? Well, n just went from being 2 to 3. And the bottom line is any decent sized number squared is much smaller than any decent sized number cubed. So you just got a lot bigger by going to this, adding this orientation. What's kind of cool, by the way, and this was in the original arbitrary shapes paper, you could also do this for, say, scale. Suppose the scale was unknown. Our algorithm looks stunningly similar for each edge point, but now instead of having a master theta, all right, we have a master scale. So for each possible master scale, we again compute the gradient direction. We again retrieve the displacement vectors, but now we have to vote with the scaled displacement vector scaled by s. And again, we vote. Whichever gets the most votes is the right point. And the peaks in this space, and now the space is x, y, and s, where s is the scale. So again, it's cubic. Now you can imagine that if you had scale and orientation, that would be quartic. That's raised to the fourth. Modest numbers raised to the fourth power are brutal. So you have to be careful in terms of how you do this.